Hi, this video is an instructional lesson on graphing the inverse function 1 over x. So if you take a look up here on the left, we have the function f of x equals 1 over x, and we are going to be working with understanding the graph of this and then understanding how to graph other inverse functions that are transformations of 1 over x. So it says you're going to have to complete the table, graph the points, and connect, and find the domain and range, and then answer the follow-up questions. So to get started, we'll go ahead and think about 1 over x and what possible values we could have for 1 over x. So we've been using, for the other functions, the point 0, 0 and testing that out. So let's consider that. If we were to create a table of values, and we let our input value be 0, then we would substitute and have 1 over 0. Well, hopefully remember that division by 0 is not possible. I'll put up here NP for not possible, so we can't let 0, 0 be a point on our graph. But could we have the point 1? Well, sure. 1 over 1 would equal 1. Could we have the point 2? Well, 1 over 2 would equal a half. So we could have, if our input value is 2, our output would be 2. So then you might think, well, could we go in the negative direction? Well, if we input a negative 1, we would have 1 over negative 1, which would equal negative 1. So sure, that would work. And so on. If we had 1 over negative 2, then that would be negative 1 half, so that could work as well. So is there really any limit to the possible x values with the exception of 0? Well, what if we had an input value of positive 100? Well, then we'd have 1 over 100, which is 1/100th. So that does have an input value. But interestingly, that's really tiny. So it looks like as our x values get bigger and bigger, our y values get really tiny. Let's see, what if we put in 10,000? Well, then we would have 1 over 10,000, and that would give us 1/10,000th. Let's see, so point, that's tenths, hundredths, thousandths, 10,000ths. So we actually would get a really, really tiny number, but we know that it can't ever equal 0. Is there any number for x that would make it equal 0? I don't believe so. We wouldn't be able to, for any value, we could not come up with an x value that would make the function's value equal 0. So there are no values. So what we see is that x gets larger and larger and larger, the output value gets increasingly smaller. So that means it's going to be approaching a limit. And that actually happens on the negative side also. If we were to put in negative 10,000, then we would get negative 0.00001. All right, so let's think about building the graph out of the points we were able to create that are convenient to graph. So if we put in 0, we couldn't get anything. But if we put in 1, we output 1. If we put in 2, we output a half. If we output 3, we would get 1 over 3. And likewise, going in the negative direction. If we input a negative 1, we get negative 1. If we put in a negative 2, negative 1 half. And negative 3, negative 1/3. So if we think about what that might look like on our graph, I'm going to put coordinates but not connect them here from our table. We've got negative 1, negative 1. We don't have 1 at 0. We have 1 at positive 1, 1. We have 1 at negative 2, negative 1 half. We have 1 at negative 3, negative 1/3. If we had 1 at negative 4, 1 over negative 4 is even closer. So you can see what's happening is as we input values, think about 1 over 10 would be 0.01. Man, that's really close, but it's under our x-axis. If we were to think about inputting values between 0 and negative 1, say for instance we thought about negative 1 half. Well, if we had 1 over negative 1 half, a half goes into 1 twice. Think a dollar divided by 50 cents. So that would actually be -2. So if we put in -1/2, we actually get a -2. If we put in, let's see, -1/3, we're going to end up with -3. So -1/3, -3. And what we see is it's actually happening in between 0 and 1, but it's approaching and getting closer to the y-axis. So what we notice is we have what we call asymptotic behavior, meaning we have asymptotes in our graph. So if we think about what that means, if we now go to our calculator and type in 1/x, we get something very interesting looking. We can see, just as we plotted, that it seems to approach the y-axis from the left side and approach the x-axis above here, or below the x-axis in quadrant 3. And it appears it does likewise in quadrant 1, approaching the y-axis for x values in between 0 and 1, and for x values greater than 1, approaching our x-axis. So if we consider our table, let's see what we notice. By looking at our table, that verifies that we can't have 1/0, so we see an error message. So on my table here, I'll just put in E for error, or error there. But let's see what happens. As x gets larger and larger, our y values get smaller and smaller. Smaller and smaller and smaller. In fact, eventually we're just going to have 0.0000 with numbers after them. So it gets increasingly smaller here. And here it went into 0.00. So what we notice is that our values for x are going to get closer and closer and closer. Excuse me, our values for y will get smaller and smaller and smaller, approaching but never touching the x-axis where our output value is 0. And likewise, it will do the same for x values that are in between 0 and 1. So if I have it start at 0, but then I change our table to, say, 0.01, let's see what happens as our x gets larger, approaching 1. We can see that if we put in 0.01, meaning 1 divided by 0.01, think about it like a dollar divided by a penny. There are 100 pennies in a dollar. So for 0.1, our y value is way up here at 100. But then it quickly starts to get closer to 0. See, it's decreasing as we're approaching 1, getting closer and closer and closer to 0. Let's see, we're at about 70 cents, 0.7. Let's see. Oh, man. We're getting closer to 1. All right, so now we're at 1,1. But then after 1, it's getting closer and closer to 0. So we have an asymptote on both sides, or for both portions of our graph here. And I'm going to highlight them so you'll be able to see them instead of drawing over my x and y axis. But we make asymptotes a dotted line because if we were to make them solid, it would mean that they are officially a part of the graph. And they're not a part of the graph. They're like invisible boundary lines where the function gets closer and closer and closer to that value. And of course, the equation for this asymptote would be y equals 0. The equation for this vertical asymptote here on top of our y-axis is x equals 0. So remember, equations of horizontal lines are y equals, equations of vertical lines are x equals. So this would be what we call a vertical asymptote. For here at x equals 0, and here we have a horizontal asymptote. Like that. Okay, horizontal asymptote and vertical asymptote. So really, the points that I'm going to need to consistently see on your function are the points 1, 1 and -1, -1. And then after that, you can just make sure your graphs are approaching your asymptotes. So very important to understand the asymptote concept for these two functions, for this particular function. Now, if we were to consider our domain, remember our domain is our lowest x to our highest x, and we ask ourselves, does our graph go left and right forever? Well, it does appear to be going left forever and right forever. However, we know by looking at our table and by understanding that we cannot come up with an x value where our output is 0, that we never have a point on our graph where our y coordinate is 0. So it's kind of like if you were to think about on a number line, let me see for domain. On a number line, if you were to have 0 here, it's like x can be greater than 0, and x can be less than 0. It just can't equal 0. So it's like having an open circle there. Well, if we were to write an inequality to represent that, we would say that x is less than 0 or x is greater than 0. Well, in interval notation, all you do is know that you're going to have two intervals showing that you skip over the value of 0. So your domain exists from negative infinity up to and not including 0, so we use that 0 exclusive, union, but then it picks up after 0 and it continues on to infinity. So our domain would be negative infinity to 0 exclusive, union 0 exclusive to infinity. Our range, if we were to think about that similarly with our y-axis, our graph exists everywhere except 0 also. So if we think about this like a number line, again at 0 we would have that open circle. This would be positive infinity and negative infinity, representing this y-axis right here. And it would be from our lowest to our highest, negative infinity up to but not including 0. So 0 exclusive, union, and again picking up after 0 and going on to infinity. So our domain and range are just alike for the parent function 1 over x. Next I ask you to write a verbal description of what you see. So what we need to understand though is we have vertical asymptotes, but where are they? For rational functions, they're going to be at the values that would make our denominator equal 0. For the case of 1 over x, if x equals 0, then that's where our asymptote is going to be, because 1 over 0 is not possible. So let's write down here that we have a vertical asymptote at the values that make the denominator equal 0. We also we can also state that our graph exists in quadrant 1 and quadrant 3, where the function approaches but does not cross the asymptotes. Okay, the function will approach but not cross the asymptotes. So hit pause if you need to get all that down, but I'm going to move on. So we're going to move on to 1, and I ask what observations can you make about the graph of an inverse function? You can basically, in addition to this verbal description, state that, yeah, we know it exists in quadrants 1 and 2, but that the left and the right side approach but never cross the x and y axis. Alright, what x and y values does the function approach but never reach, and why? So, if you think about 1 over x equaling 0, if you think we're thinking about solving that, then we would get 0x equals 1. And if we were to divide both sides by 0, we would say, well, hey, 1 divided by 0 is not 0. It's actually undefined. Therefore, there are no input values that could make the denominator equal 0. DEN for denominator, okay? X is undefined for a value that would equal 0, okay? Why do you think the graph is only in quadrants 1 and 3? If you think about it, if we were, for all positive input values that we put in for X, we got a positive Y. However, for the function 1 over X, if we put in a negative X value, we got a negative. So why do you think it's only in quadrant 1? Well, 1 divided by a positive is positive. 1 divided by a negative is negative. But then it does ask, how could you make the graph appear in quadrants 2 and 4? So if you go back to thinking about this graph up here and what we know about other functions, if we wanted to switch those and make them appear in quadrants 2 and in quadrants 4, then with other functions, we've had a negative a value. So let's consider that. So let's see, if we want to switch quadrants, if I type in a negative 1 over X, let's see what the graph would look like. Oh, that does appear in quadrant 2 and in quadrant 4 by putting a negative. Okay, so to do that, we would need to make a negative. Making the function, and we'll define it a in a minute, a negative number. So if we make a negative, then it will reflect and be in quadrants 2 and 4. Hit pause if you need to go ahead, otherwise I'm going to continue. So the next thing you're asked to do is to be able to graph these using transformations, defining the domain and the range. So if just to get started, the first one is negative 1 over X, which we've already talked about. So if we've got negative 1 over X, we saw that it just simply made it reflect. Thinking about points, if we're not doing anything but reflecting, let me go back to setting this at 0 and at 1. Then we'll see that we still have a restriction on 0. However, we still have the point negative 1, 1 and still have the point 1, negative 1. Or in other words, the 1, 1 and negative 1 actually invert. So instead of being here and here, they're going to switch to here and here. So 1, negative 1 and negative 1, 1. We should still indicate that we will have asymptotes by putting in dotted line on our x and our y axis. In a few minutes, we're going to be shifting those asymptotes. But all you'll need to do from here is sketch indicating that the graph gets closer and closer to these asymptotes, but never touching or crossing. And make sure you put an arrow on the end. So as long as you've got these 2 points, that's what we're going to be looking for when you graph. Your domain, it goes left and right forever, skipping over 0, so similar to 1 over x. Our domain, I'm going to write it above since it's going to be a little longer, is negative infinity to 0, union 0 to infinity. And I should say 0 exclusive. Our range on the same order from negative infinity up to, but skipping over 0, starting back over it after 0 and going on to infinity, so it'll look the same. Okay? Hit pause if I'm going too fast, but I'm going to basically move on to number 2, and if you notice we have 1 over x plus 3. So what I want you to do is relate this to what we've already talked about with the square and cube root functions, is a function in the form y equals a over x minus h plus k. So as you can pretty much guess, if we were to create a function for this in this form, we would probably have a -1 on top. We notice that there are no other values, so we should assume 0. But we could make it look like this function here, or like this form, recognizing that the 0, 0 is actually the intersection of the asymptotes. So let's make sure we define what that is, because h and k mean different things for different functions. In the case of the inverse function, h and k is the intersection point of the horizontal and vertical asymptotes. So h and k is your intersection point of the horizontal and vertical asymptotes. So for number 2, if you take a look at this, if you don't see a number, remember it's an understood 0. If I am to state h and k, please remember that this is x minus h, so this must have been x minus a -3, which makes our h value -3. Or think of the whole switch keep concept. +3, think -3, keep the sign of any constant out here outside. So that means at -3, 0, I'm not going to use a pen, which I'm using to graph my function. I'm going to use my highlighter. So I'm going to go to my x value of -3, 0, and at this point, I'm going to use it as a guide to put in my horizontal and vertical asymptotes. So -3, 0, easy enough, graph your asymptotes. If there is a negative up top, then that tells you want to use quadrants 2 and 4. If it's positive, then you're going to use quadrants 1 and 3. So think, even though this isn't technically quadrant 1, think of it as the quadrant being divided by your asymptote. So this would be the upper right side and the lower left are the two regions that you need to use to graph. So to graph this, there's nothing to indicate that I would not use an a value of 1, meaning from my intersection point of my asymptotes, I'm going to go right 1 and up 1 and put a point. I'm going to go left 1, down 1 and put a point. And I'm simply going to, again, make my graph approach but not cross my asymptotes that I've created here. Okay? Now this time we need to pay attention and realize that we skipped over the x value of -3. So I'm going to just put a circle there. It's not really going to affect my graph because it's not part of the graph. But maybe that will help you to think about the number line created for our domain, similar to how I showed you on the notes. So it is coming in from the left, from -infinity, is going up to and approaching an x value of -3, but it's skipping over it, so we're going to exclude -3 in our domain. Union, it picks back up after -3 and continues right forever. So all of our x values except -3. So our range is all values except 0. So if you notice, the h and k again are going to play into our domain and range that we create. So for our range, it's from -infinity up to, but not including 0, union 0 to infinity. -infinity to 0 exclusive, union 0 exclusive to infinity. Let's see, I'm going to go ahead and talk about number 5 now. I feel like you should probably be able to do numbers 3 and 4 with the given information. So now I want to talk to you about what happens when our a value, which is the numerator in this ratio here for our inverse function, our a is our value on top. So notice for all the others it was a 1, which meant that I actually went over 1 and up 1. So now let's see what happens to our graph when I type in 3 over x. So I'm going to go back to my calculator and choose 3 over x. Now if we think about a value, a set of values, if I input a 1, 3 divided by 1 is 3. And if I input a -1, 3 divided by -1 is -3. And that's how it should go. If I put in a 3, 3 divided by 3 is 1. And if I put in a -3, 3 divided by negative 3 is negative 1. So let's see what happens to our graph. So it pretty much doesn't look much different than 1 over x. So let's compare it. So let's see, what does 1 over x look like compared to 3 over x? Now it's graphing 1 over x. So you can see that it's just closer in to the intersection of our asymptotes because it contains the point 1, 1 and negative 1, negative 1. Whereas this contains the point 1, 3 and negative 1, negative 3. And we can verify that on our table. I'll go ahead and take out the 1 to the x so you don't get confused. Looking at our table, there we go, negative 1, negative 3, and 1, 3. We can pick up some other order pairs if we want. Let's see, 3, 1. We already talked about these points, actually. All the other points are going to be decimal values. So all I need you to do is, again, recognize that if you don't see any other numbers, our h and k are 0 and 0. And that, again, is going to represent the, it's going to represent the intersection points of our asymptotes. So at 0, 0, I know I'm going to have asymptotes. The only difference is now I'm not going to plot 1, 1. I'm going to plot 1, 3. So just think all you're doing is stretching your y values by 3. So that means when I graph this, I'm going to make my function approach but not cross my asymptotes. All right, domain again, and range. All right, so I'm going to do this number 6 as the very last example because this video is already closing in on 30 minutes. So number 6, notice that we have several different things going on. We have an HK value switch keep of positive 2, negative 2. That tells me that at 2, negative 2, if I were to put a point with my highlighter, that is where my vertical and horizontal asymptotes intersect. The next thing I notice going on is I have a negative. This tells me I have a reflection. So rather than my graph appear in the regions 1 and 3 here, they're going to appear in 2 and 4. So I need to put up here regions 2 and 4. And I'm calling it regions instead of quadrants. Regions 2 and 4. So that means instead of going up using this area, I'm just going to use this instead. Instead of down, I'm going up. Instead of up, I'm going down. But now my A value is 4. So that tells me I need to go over 1 and up 4. Oops, I'm going to do it backward. It's supposed to go down 4. Over 1 and 1, 2, 3, 4. Then over 1 and 1, 2, 3, 4. All right. Then after that, I really just need to see you go ahead and graph them. As long as you've got that point, that's what we are going to be looking for, is the correct point here, an A value of negative 4. Okay? And domain, of course, we're skipping over a value of positive 2. So you can look here at your H to help you out. But that means it exists from negative infinity to 2, exclusive, union 2 to infinity. While the range, again, I'm using the K value, would be, it exists from negative infinity up to, but not including negative 2. So exclusive, union, pick up after negative 2 and go on to infinity. All right, that concludes your lesson on the inverse function. Please go ahead and complete the graphs of 3 and 4. Thank you.